Welcome back for part 2 of the gravitation video series. So we just took a look in part 1 at the acceleration due to gravity and how it depends upon distance and how it's actually a vector quantity because it is an acceleration. And then we took a look at the idea that if you were to go inside the center of the Earth somehow or under the crust of the Earth, that you would actually decrease gravitational acceleration and therefore you would your max value would be at the surface because that's when all of the mass is on one side of you. You're technically tangent to the circle at that point. And at that point, you would decrease to zero once you got to the middle. Let's take a look now at the gravitational potential energy that we worked out some of in class, but we didn't quite complete it. And for that, I do want to kind of get back to that idea of the gravitational acceleration being a vector, because there was a little bit of, let's say, consternation that the integral was being shown as we have it here. And let's go ahead and walk through what it was. We did go through this in both classes, however, I want to review it a little bit. That we need to set a place where the gravitational potential energy will be zero. And the potential energy for, classically, when we're dealing with objects near the surface of the Earth, we say is mg times y. That at any given point relative to some zero, which we typically say is ground level, the potential energy would be the mass of the object times the gravitational acceleration times the position. Well, when we're dealing with astronomical scales or galactic scales, as I believe I have it written right there, both the position and the gravitational acceleration vary. And the position increases linearly with position, because that's the position. The gravitational acceleration will decrease, not linearly, but it will decrease as an inverse square. So if we double the position here, the gravitational acceleration will actually be 1/4. So we double one, we get 1/4 of the other, we end up having half the energy overall, and that will continue, that pattern. And instead of trying to do some sort of numerical approximation of it, we can do an integral to figure out what the actual relationship is. So we took a look at gravitational potential energy being the integral of force with respect to distance. And we said, well, what would it take? What sort of potential change could we cause if we exerted a force pulling something from an infinite distance back to the back to the surface of the Earth? And the reason we went in that direction was we were saying we had to set a 0 point. Gravitational potential energy needs a place where we can say there's no energy, no tendency to want to go into motion. And in a typical situation, we just call that ground level. We make the position 0 height, the ground, the tabletop, whatever it is our kind of lower vertical position. However, that's not technically 0. That's just an arbitrary thing that we set. So where there's 0 potential is where there's supposed to be 0 tendency to want to go into motion. For us, that would be at an infinite distance from a planet. Now, this is just a gravitational potential energy from that one planet, not from all planets, just from the one planet. So if we set r is equal to infinity, g would be equal to 0 as a limit, which means there's no tendency to accelerate. So infinite distance from a planet is really where there's 0 potential energy. So if we want to pull something from an infinite distance back to Earth, then we would integrate from 0 to the radius of that planet. Now this caused, as I said, a little bit of consternation. So let's go ahead and take a look at it from a slightly different point of view. So my scrolling seems to be taking forever. We defined work as the integral of force as a vector dot product with dr as a vector. That was the original way that we defined what work was. And this was work done by some external force. So that was you, me, friction, something exerting a force on an object, and we have force as a function of position, or it could be a constant that gets pulled out. But this was external work being done. And if I exerted an external force on an object, I could give it a greater potential energy. I could give it kinetic energy. We said that the work done, if it was a net force that was causing that work, would end up changing the energy of an object. We also said that if you were to do work from a conservative force, conservative forces always wanted to try to minimize potential energy. So for instance, an object that was falling due to the force of gravity, it would have a displacement, r, that was in the same direction as the force. That would yield a positive amount of work, because the force and the displacement are parallel with each other. However, that work would also lead to a decrease in the potential energy of the object. It had more potential energy high up than it did down below. So where we could say that work from an external force, from you, me, etc., could positively or negatively, depending on which way we wanted to say we're pushing, change potential energies, we'd have to know some context. Conservative forces were always going to try to minimize the potential energy. The spring force tries to pull a mass closer to the origin. Gravitational force always tries to pull something closer towards the center of a planet. So conservative forces would do work that is equal to negative change in potential energy. Now, if there's one of those two potentials at zero, then we could just say that the work becomes negative energy at some position. If we couple that idea with saying that work from a conservative force is equal to negative change in potential, and we say that the potential should be the integral of whatever force it is we're looking at. If we're talking about gravitational potential energy, we'll use a gravitational force dot product with dr. Sorry, I have my cursor over the top of that. The gravitational force, the conservative force, is going to try to pull something not from the surface of the planet away to infinity. It's going to start out with the object at an infinite distance, and it's going to pull that object towards the surface of the planet, towards a radius value r. So let's go ahead and do this integral this way, but reminding ourselves that the acceleration due to gravity, I'll scroll back over here. The acceleration due to gravity as a vector is negative of the radius direction, and the force due to gravity is that acceleration multiplied by mass. So as a vector, the force due to gravity is negative g m times little m over r squared, and then the radius unit vector. There it goes. It's taking a while to load up. So if we put those into our integral, negative delta u equals integral from infinity to r of negative g m over r squared dr. The negative signs that we have right here end up canceling each other out, and we're left with the same integral that we did before. So just taking a slightly different approach, this was simplified, this is more accurate, we end up getting the same integral. And if we process that, we get a change in potential energy that will be equal to negative g mass of the planet, mass of the object, over r squared. So we get the same result, just from a slightly different approach. Maybe one that's a little bit more realistic and less simplified. Now, as we were discussing in class, the usage of this equation could tell us how likely something is to go towards a planet if it's some distance away. The oddity, of course, is that it's now a negative value. But in terms of an absolute scale from an infinite distance away towards like negative infinity, as we go from that infinite distance down towards the surface of a planet, we should decrease our potential energy. And on an absolute scale, going from zero energy to a negative is technically subtraction. We're losing potential energy that can then go to kinetic energy. Now, for the escape velocity, we want to figure out if we've got some potential energy at a location and the kinetic energy. What if we had so much kinetic energy that when the object went flying away, it never came back? That as it moved further and further away from the surface of the planet. Draw a little circle here. Let's say it's right here and it's got some velocity v. As it moves away, that velocity should decrease. But as the velocity decreases, the acceleration of gravity it experiences is also going to decrease. And as it moves farther and farther away, and the velocity keeps getting smaller and smaller, the gravity also gets smaller and smaller as well. So at some point, it's going to have nothing trying to slow it down, but it's still in motion. And if that velocity initially is really, really big, like 10 times as big, it should be able to go even farther before it finally would want to come back. To the point where if the velocity is some specific number, it should be so fast that it can never return to the planet. That it's got more kinetic energy than potential energy to take it back down. That velocity is what we call escape velocity. And if we set this equation saying that it gets to a point in space, some infinite distance away, where it then comes to a stop. At an infinite distance, it should have zero potential energy. And if it comes to a rest at that exact point, infinite distance away, it'll have zero kinetic. So it'll run out of energy completely at some infinite distance. And if it goes faster than that initially, it'll go even further than infinity. That's kind of weird to think, but we're dealing with limits here. So we say that the two energies together will add up to zero. We can then solve for the velocity that you require, and we get this equation right here. Square root of 2 universal gravitational constant, mass of the planet, and radius of the planet. Or not necessarily radius of the planet, but position that it starts at. Typically, we think of escape velocity as leaving from the surface of the planet. So if you get this value, which by the way we can calculate for the planet Earth, it's somewhere around 11,000 meters per second, it's very large, you will not return. You will go off forever. So let's take a look at this example problem connected to that. It says Earth has an escape velocity at its surface of v. Suppose you were on the planet, on the surface of a planet with mass 2 times that of Earth and radius 1/2 that of Earth. What would be the escape velocity from the surface of this planet? So take a look at this equation and try to determine what that new velocity would be in terms of v. I'm going to pause it here. You should pause it, and then we'll reveal the answer in a second. So if we take a look at the original equation here, that square root of 2gm over r would be the escape velocity, we're going to put a factor in front of the m and the r, twice the Earth's mass and 1/2 the radius. So it's a very dense planet. If we were to make those adjustments, and what we ultimately want to do is see how those affect the original. So we want to maintain all of these variables and then just have some extra numbers. So I've got a 1/2 on the denominator that kicks up here to this 2 to make it a 4. And then, well, I got a 2g and m and r and like an extra 4 in the radical. So I can just square root that, pull it out as a factor of 2. So we have essentially twice the original escape velocity. So whatever it took to escape Earth, you got to go twice as fast if you're going to launch from the surface at that instant with that speed in order to escape the planet forever and never come back. All right, we're going to pause here and we'll go on to a part 3 where we talk about, well, orbits. Orbits are cool.